Hey everyone! In this video, I'll walk you through how to build a financial portfolio assistant React agent. What then can actually remember past conversations using MongoDB and LangGraph checkpointers. In a nutshell, this assistant will serve as an intelligent financial advisor which analyzes user queries, fetches relevant financial data, and presents actionable insights. Throughout this process, the agent maintains a conversation state in MongoDB, enabling it to reference previous interactions and provide contextually relevant responses over time. Before continuing, I want to emphasize that the purpose of this video is not that you code parallel to me. For this matter, the full code is available on Industry Solutions Team GitHub, and you can find the link in the description below, along with all the other resources mentioned throughout the video. So first, take a look at the high-level architecture where you know some of the key features and technologies I'm using to build the solution. But before jumping straight to the implementation, let's quickly review some of the key concepts behind. On their own, language models can't take actions. They just generate text. Agents are systems that take a high-level task and use an LLM as a reasoning engine to decide what actions to take and execute those actions. LangGraph is an extension of LangChain, specifically aimed at creating highly customizable agents. Our LangGraph agent will be of the React type, which stands for reason and act. This means the agent will go through a cycle of reasoning and acting. If you want to learn more, there is a link to a scientific article in the description below. Basically, the agent will decide whether to use tools or not, and will keep repeating this reason and act process until it finds an answer for the user. It is important to note that LangGraph provides a set of pre-built reusable components, which are designed to help us construct agentic systems quickly. For this use case, I'm using the create_react agent function. When constructing an agent, you will need to provide it with a list of tools that it can use. Tools are a way to encapsulate a function and its input schema in a way that can be passed to a chat model that supports tool calling. This allows the model to request the execution of this function with specific inputs. The custom tools are defined to interact directly with systems, such as databases or an API. In our use case, these tools interact with the MongoDB database, performing data aggregations, retrieval, or semantic search operations by leveraging MongoDB Atlas Vector Search. All the custom tools specs are thoroughly defined over the code documentation. On the other hand, I'm leveraging the pre-built Tabili search tool to connect the agent to the web using Tabili, a search engine optimized for LLMs and RAG. This allows the agent to access real-time data beyond what the LLM the agent is using was originally trained on, and enables it to answer questions based on the latest information available. A Tabili API key is required, but you can easily get it by creating an account. The free tier is enough for this case. Now, where does the data come from? This AI agent is part of a bigger system which includes data ingestion pipelines and processing services. If you are curious, check out the other two repos linked below, and let me know in the comments if you liked a full walkthrough on those two. In the interest of time, I leave that aside and tell you that it would be enough if you import the sample data available on the repository over the MongoDB database. And yes, you can create a MongoDB Atlas cluster for free with just a few clicks. For more information, please follow MongoDB's documentation included in the description. If you take a look at the sample data, you'll notice it's financial in nature. Things like market trends, economic insights, and financial news. The React agent interacts mainly with two MongoDB collections. The report market analysis contains market analysis reports. Each document includes a report embedding field, which holds a vector representation of the report, generated by the Voyage Finance 2 model, and the report market news collection, with similar idea, but this one stores financial news article, also with vector embeddings from the same model. These embeddings are what enable the agent to perform semantic search, meaning it understands the context and meaning behind a query, rather than just looking for exact keyword matches. The Voyage Finance 2 model is optimized for finance retrieval tasks. This model understands the nuances of financial language and excels on generating efficient vector representation for financial news articles, market data, and other financial documents. We are using the Voyage Finance 2 model from Voyage AI, which is specifically optimized for financial data. It generates high-quality vector embeddings tailored for finance, like market reports and news, which is perfect for semantic search tasks in this assistant. The best part, you can use the Voyage AI API with a free trial to get started. If you are curious and want to learn more, I linked to their official blog in the description. And yes, MongoDB recently acquired Voyage AI. This acquisition helped us bring AI and database capability even closer together, so teams can build more accurate and reliable AI applications without extra complexity. I've linked this blog in the description if you want to read more. As for the chat completion model, I've chosen Cloud 3 Haiku, which runs on AWS Bedrock. To replicate this setup, you will need an AWS account with access to Bedrock models and proper credentials. That being said, you don't have to use the exact same models I'm using here. You are totally free to swap in different embeddings on chat completion models. The Asian architecture is flexible enough to support that. To enable semantic search, we use MongoDB Atlas Vector Search, powered by vector indexes. These indexes are built on fields like report embeddings, allowing us to find semantically similar reports based on user queries. Not just keyword matches, but real meaning. Now, there are two ways to create these indexes. One, you can run the vector search index creator.py script in the GitHub repo. It's quick and automated. Or two, if you want to understand how everything works under the hood, you can follow MongoDB's official documentation, which I've linked in the description. The first option is faster, but the second is a great way to deepen your understanding of how Atlas Vector Search really works. Now that we covered the key concepts, we are almost ready to jump into the code. But before that, make sure you completed the prerequisites and setup instructions outlined in the project README. I won't cover the MongoDB Atlas account creation step in detail, since I really have mine set up. But if you are new to it, just click the Register Here link in the README. It'll guide you through the process. Throughout the video, you will see me using MongoDB Compass, the official graphical user interface to explore and interact with your MongoDB databases. I highly recommend downloading it if you haven't already. The link is in the description. For dependency management, I'm using Poetry. If you are not familiar with it, you can check out their official docs, also linked on the video description. The important part here is that all dependencies and versions are defined in the PyProject YAML file. We also use a makefile with predefined commands called targets to simplify setup. In particular, the poetry_start and poetry_install commands will create a virtual environment and install all required dependencies. I won't run those commands now because I already done it. That's why you can see the .m folder created with all packages installed. Next thing is to set up the MongoDB database and collections. So I grab the names from the README and create those by using MongoDB Compass. Then I'll port proper sample data to each collection. The Asian_profiles store Asian profiles. The reports_market_analysis store market analysis reports. The reports_market_news store market news reports. The portfolio_allocation stores portfolio allocation data. The portfolio_performance store portfolio performance data. The checkpoints_AIO store Asian state checkpoints. The checkpoint_brights_AIO store Asian state checkpoint brights. Some collections are more relevant than others in this demo, but if you plan to explore the broader project, you'll need all of them. So, a friendly reminder to set up the vector search indexes for reports market analysis and reports market news collections. You can do this quickly by running the following Python script located in the backend/loaders/db directory with the name of vector search index creator py script. Make sure to parameterize the script accordingly. Follow MongoDB's guide to create a user with read-write and DB admin access to the database. This is also linked in the description. Create a .m file to set up your environment variables. You'll need to complete the values with proper connection string to access the MongoDB database, as well as keys for accessing the different services such as Voyage AI, Tabili, and AWS. For AWS, you can either use access and secret keys or authenticate using SSO, which is a more secure option. To authenticate with SSO, you can run the following command, assuming that you got the AWS CLI installed on your machine. Now, let's take a look at the code. We'll walk through the React _agent console.py script, which brings the whole implementation together in one file and lets you run the assistant directly from the terminal. That said, the repo also includes alternative scripts that implement the same core functionality using Fast API Web Framework. We will touch that later. Starting at the top, we have the usual imports. We load environment variables with .m, configure login, and initialize reach for clean, color-coded terminal output. Then we move on to the key building blocks of the assistant. First, we configure Bedrock and initialize the Chat Bedrock LLM, the model that powers our agent reasoning. Next, we add Tabili search results, which lets the agent pull in real-time information from the web when internal sources aren't enough. Then we set up our embedding model using Voyage AI. This lets us turn queries and documents into vectors for semantic search. We also connect to MongoDB twice, initially for accessing pre-computed market analysis and news reports, then again later inside main line 519 using async MongoDB saver for long-term memory and checkpointing with LangGraph. That's because the early stage data fetches are fine with a synchronous connection, but memory and checkpointing needs async support for non-blocking performance. After that, we define some utility functions. Generate thread ID function creates unique IDs using timestamp. List available threads function lists past conversation from memory, helpful for stateful interactions. Clean up old threads. Let us programmatically clean up older LangGraph checkpoints in MongoDB. These are specifically useful in memory-constrained environments. Now onto the interesting part, custom tools. We define two vector search tools. Market Analysis Report Vector Search Tool retrieves insights from our semantic vector database of market analysis reports. Market Analysis Reports Vector Search Tool does the same but for news articles. Both tools are decorated with LangChain's @tool decorator, which exposes them as agent actions during planning. LangGraph then used this to decide what the agent should do step by step. This is how the React agent works when using at least one of those two tools. It receives a query, embeds it using Voyage AI, runs a vector search pipeline in MongoDB, and returns an structured summary back to itself for reasoning. Now, this is the most complex part of the code. We define a function to process chunks from the agent. Why? The agent will return chunks with a lot of information. We want to extract the most useful information. If the agent decides to use tools, we extract the tool name and the tool query and display an informative message. If the agent decides not to use tools, we just display the agent's answer. This function handles memory checkpoint from LangGraph. It goes through past interactions saved in MongoDB and pulls out relevant information. Each checkpoint consists of a tuple where the first element is the index and the second element is an object containing various details about the checkpoint. The function distinguishes between messages from the user and the agent, displaying them accordingly. Now we get to the heart of the script, the main function. This is the entry point of the app and manages the entire chat lifecycle. First, it loads the MongoDB credentials from environment variables and sets up asynchronous connections, crucial for non-blocking I/O when using LangGraph's persistent memory. Then, as mentioned earlier, we initialize the async MongoDB saver, which will be responsible for storing and retrieving memory checkpoints across sessions. Once setup is done, the assistant welcomes the user and offers 3 options: start a new session, continue with a previous session, or clear all memory. If you choose to clear memory, it confirms before wiping all checkpoints from MongoDB. Behind the scenes, the script generates a unique thread ID for every new session using timestamps. It also uses list available threads and clean up all threads functions to keep memory lean, only keeping a few recent sessions to avoid clutter. Next, we create our LangGraph React agent by calling createReactAgent function and passing in the language model, the tools, Tabili plus our 2 vector search tools, and the memory checkpointer, backed by MongoDB. This set up the full planning plus tool using agent flow. From here, we enter the chat loop. It goes like this. The user types a message or question. If they type quit, we exit. If they type clear all memory, we confirm and clean up. Otherwise, we send a message to the agent using the aStream method. If the agent doesn't need any tools, it simply uses the LLM to generate a direct response. But if the agent does need tools, it enters the rationing and acting cycle, leveraging the tools we defined earlier. Each step, every tool call, rationing step, and final answer is streamed to the terminal in real time for transparency. Once the response is complete, we fetch and display the latest memory checkpoints using process_checkpoints function. This gives us a full traceability of the session. Thanks to long-term memory, every thread is persistent and reusable. Let's run the example. First, we will type something generic, a message the agent won't need tools to answer, something like, "Hi, I'm Julian." As you can see, the agent didn't call any tools and simply greeted us. The console output is very verbose. That's intentional. It shows detailed information from the checkpointers to help us better understand how the agent's memory is being tracked. Next, let's try something more specific, a question that will require the agent to use tools. Something like, based on market conditions today, what overall portfolio asset relocation would you suggest? This time, the agent used the Market Analysis Reports vector search tool with the query portfolio asset relocation based on current market condition. Then we can ask, what's the news sentiment about my asset gold? Now the agent switches to the other custom tool, Market News Report vector search tool, with the query news sentiments about gold. Let's quit this chat and run the last example using the integrated UI, which will make things even clearer. In this third example, the question requires real-time internet search. Let's ask, I would like to start investing in the database market. Can you search the internet for what's going on with MongoDB? I want to know what the press is saying. Here, the agent uses the Tabili search tool with the query MongoDB News. As mentioned earlier, this component is part of a larger system. If you want to explore the UI integration, definitely check out the Industry Solutions team GitHub. You'll find a link to the front-end repo in the description below. Last but not least, let's run the agent again in the terminal to explore other menu options. This allows the user to continue an existing session or clear all chat memory. For example, I'll select option 2. Then choose one of the available memory threads. Now I ask, what questions have I asked you so far and which tools have you used to respond to me? You'll notice the agent is able to provide a summary because it's aware of previous interactions stored in that memory thread. Mind-blowing, isn't it? Thanks for watching. If you found this video helpful, please give it a like and drop a comment.